In this lecture, we will introduce the notion of predicate. We will explain how to specify predicates, their syntax, and we will explain how to interpret predicates, how to compute a truth value given a predicate. So that's the semantics of predicates. Recall that we have explained the semantics of propositions by considering them as little programs for a device that takes as input a truth value or several truth values and produces a truth value as output. We can continue with this analogy and refine it a bit when discussing predicates. A predicate is also a program for such a device, but now the device may have different kinds of input. It need not be a truth value, it could also be an integer, as you can see over here. So this device, programmed with the predicate 4x less than 5, will take the integer x, multiply it by 4, and compare it with the number 5. And if the result is true, then it will output the truth value true, and otherwise it will output the truth value false. So, for instance, if we input the integer 0 to this device, then it will evaluate to the truth value true. Whereas if we input an integer 3 to this device, it will output the truth value false. We can represent the interpretation of this predicate by drawing a one-dimensional graph, as you can see over here. So a unary predicate takes a thing of a certain type as input and produces a truth value as output. Now, the type of the thing that it takes as input is important. We could just as well consider the same predicate 4x less than 5, but now say that the input is not of type integer, but is of type real. And then we could also use this device to evaluate the predicate for values that are not integers. For instance, -1/2 times the square root of 2, which makes the device evaluate to true, or pi, which makes the device evaluate to false, or the fraction 5/4, which makes the device evaluate also to false. And then, of course, when we draw the interpretation of this predicate, we should use the continuum, we should use the whole real line. Using variables to name input of our predicate has the advantage that we can now easily generalize and specify predicates relying on more than one input. In this example, we see a predicate that needs 2 inputs before it can be evaluated. The device programmed with this predicate multiplies the input x by 2, adds y, and compares the result with the number 2. We see here how a complex predicate is specified using the simple predicate greater than, the operations for multiplication and addition on numbers, and a constant, the number 2. The behavior of the device with 2 inputs is visualized using a 2-dimensional graph with real numbers on the x-axis and natural numbers on the y-axis. With every valid point in this graph, that is a point with a real coordinate, a real x-coordinate and a natural y-coordinate, we associate a truth value. As usual, points colored red are points with the truth value false associated with them. Points colored green have the truth value true associated with them. For instance, inputting 1/2 on the x port and 3 on the y port of the device yields true, whereas inputting -1 for x and 2 for y yields false. Here's the definition of the notion of a binary predicate. A binary predicate takes 2 things of certain types as input and produces a truth value as output. We have already seen how complex predicates can be built from simple predicates, less than, operations, multiplication and addition, and constants. It is also possible to build even more complex predicates using the logical connectives we know from propositional logic, and also later using quantification. For instance, we can combine the 2 predicates 4x less than 5 and 2x plus y is greater than 2 using a conjunction, as you see over here. The resulting binary predicate can be visualized again with a graph. The graph combines the requirements that 4x should be less than 5, and hence x should be less than 5/4, and furthermore, 2x plus y should be greater than 2. We can now present a general definition of the notion of predicate. A predicate takes a certain number of things, of fixed types, as input, and produces a truth value as output. We've seen examples of unary predicates, which take 1 input. We've also seen an example of a binary predicate, which takes 2 inputs. And just the same, we can imagine ternary predicates taking 3 inputs, and so on. Well, what you should remember is that a predicate has a fixed number of inputs, and the inputs are indicated in the predicate by means of variables. And there's one special case still that we could add. We also consider nullary predicates, which take 0 inputs, and actually these are propositions. Thinking of a predicate as the specification of a device that takes input of a certain type and produces a truth value as output, you can probably imagine that different predicates may result in the same behavior of the device. For instance, when we draw the graph associated with the predicate x greater than 1 or y greater than minus a half x plus 2, then we may notice that it is identical to the graph associated with the predicate 2x plus y is greater than 2. We can therefore not distinguish devices programmed with the predicate 2x plus y is greater than 2 and with the predicates x is greater than 1 or y is greater than minus a half x plus 2 on the basis of their behavior. The predicates are said to be logically equivalent. Here's the definition of logical equivalence for predicates. Predicates P and Q are logically equivalent if for every assignment P evaluates to true if and only if Q evaluates to true. You may observe that the definition of logical equivalence for predicates only deviates from the definition of logical equivalence for propositions in that P and Q are understood to be predicates rather than propositions. For the rest, the definitions are literally the same. For logical equivalence on predicates, we also use the same notation as for logical equivalence on propositions. To illustrate that the types of variables in predicates are important, and also to illustrate the notion of logical equivalence, let us return to the example with which we started the lecture. We consider the predicate 4x less than 5, assuming that x is an integer. In that case, the predicate 4x less than 5 is actually equivalent to the predicate x less than 2, as you can also see from the graph. On the other hand, if we assume that x is a real number instead of an integer, then the predicate 4x less than 5 is not equivalent to x less than 2, as you can see again from the graph. But the predicate 4x less than 5 now is equivalent to the predicate x less than 5/4. This concludes our introduction of the notion of predicate. In the next lecture, we will introduce quantification.